Okay, this is my last recording for this online semester. I can't say I'm sad. It's kind of stressful to record and just talk to myself. But we're going to talk about half-lives. So I'm going to share my screen with you. Let's see here. Do a quick little, this is in the notes. I don't think this is in your unit workbook quite yet. So just half-life, what does it actually mean? You guys did this in earth science, actually. And if you had Mrs. Pratt, you're doing it exactly. She did it the same way that I do it. So hopefully it'll be pretty straightforward. So half-life, it's a constant. It cannot change. You can add as much heat as you want to, put on as much pressure as you want to on that radioactive isotope. Its half-life stays the same. So there's a list of half-lives on table N. And it tells you, that time tells you how long it takes for half of the sample to transmutate or decay into something new. So when we were doing our nuclear reactions, and if you go back to, let's see, page 3, right, we did beta. That's a beta reaction, and cesium transmutated into barium. So let's say cesium's half-life is a minute. Well, if cesium's half-life is a minute, then half of whatever we started with would become barium within that minute. So there's a big fluctuation between half-lives. They can be really short. So like fluorine-17 has a 70-second half-life, whereas uranium-238, which is, you can find that in your countertop, is, what is that, billion of years, whereas carbon-14 is right in between, you know, not as big as the billion, but, you know, many thousand. So the longer the half-life, the worse it is for the environment. So when we think about those nuclear fuel cells, generally speaking, we've got uranium-235, which is still pretty close to 1 billion years. It is on table N. I can't remember the number right off the top of my head. But when we're also looking at things that we use diagnostically for detecting cancers, those half-lives, like fluorine is too short, right? 70 seconds, that's not enough time to actually get an image, because what happens is these radioisotopes enter your body, they do a reaction, they produce energy, and that's the energy that can be detected. So we need it to be long enough so that it can be detected, but then of course short enough so that you're not radioactive for a really long time. So like iodine-131 has a half-life of about 8 days, and that's a very fair amount of, you know, a good amount of time to do diagnostics. And that's what we use to detect thyroid cancer, actually. So we can look at half-life. So we know the number of half-lives, right? Because that's the amount of time that it takes. In this case, we're looking at strontium-90. So when it's 100%, no time has gone by, no half-lives have gone by, it has not decayed to anything. Its half-life, so one half-life has gone by in 28 years. So now 50% of it's remaining. 50% of it has transmutated or decayed into something else. After another 28 years, I'm at 56, so 2 half-lives have gone by. Half of it remains, and now it's the rest of it, that other 25%, has become something else, and we go on. So when we graph this, you can see, like back here, it was about 28 days, and here, if I look at 50% on my curve and I drop down, yep, I get about 28. This is a little bit weird. Looks closer to like 30, but it's close to what we just said. This is a logarithmic scale. So, no, it's not. It's exponential decay, sorry. This is exponential decay, so it will never hit 0. So once something's radioactive, it is always radioactive. Okay, you guys have this on the top of page 10 in your unit workbook, and it goes through the calculation. So no matter what the question, I always set up this chart. So my mass, what it tells me in the problem, initially, and this is the part that kids forget, I have to start with 0, 1, 0. Have to. Because initially, right, no time has gone by. I have the whole thing, so it's not a fraction left. It's the whole thing, and no half-lives have gone by. But then as I decrease, right, I know over time, and in this case for potassium 42, if you look it up on table N, it tells you the half-life is 12.4 hours. Then in that one time frame, half of it will decay into something else, and I will have only 160 grams left of the original potassium 42. So now half of it's gone, one half-life has gone by. I keep decreasing my mass by 2. So I'm always dividing by 2 in this column, and I'm always adding the half-life time in this column. So I'm going to do that until I get to 62 hours, because that's what the problem says to do, right? It says, hey, you know what? At 62 hours, we want to know how much is left. And then my fraction, you'll multiply the denominator by 2 each time, and the half-lives, you're just always adding 1. So in this case, my answer is right here, 10 grams. That's my answer. Okay, so that's how you do it. I'm actually going to stop sharing this and go to your unit workbook, because that has what I need. So, hang on a moment, sorry. Okay, so here is my half-life. So I'm at the about middle of the way through on page 10. It's talking about right here, this. I'm going to do it down here though, just because there's a chart, it makes it a little easier, and I can just fill in the blanks with numbers. Now, because of the way the question's phrased, right, it's just asking me for how many half-lives, and it does not give me a mass. So that means if I don't have a mass, I can't do any of this down here. So this is all just one big X. Can't do it, not going to do mass, not going to happen. And you could go all the way down. Time, I still have to start with 0, 1, 0, okay? Because initially no time has gone by, I have all of it, no half-life has gone by. When I look, or it tells me in the question that it's 3.82 days. So after my first half-life, 3.82 days have gone by. I now have half of it left, and that's just one half-life. Now you need to know when to stop. And in this case, it's asking you to stop after 11.46 days. So I'm not there yet. I'm going to add another 3.82 to this to get 7.64 days. Now I've got a quarter of it left. 2 half-lives have gone by. And then when I add another 3.82, I get 11.46. That's my tip off right there. That's my stopping point. I have 1/8 of it left, and 3 half-lives have gone by. Now, one of the problems is once you've done this, you're like, oh, I've got my answer, I'm good to go. But if you just leave it like this, I'm not sure what number represents your answer. So you want to definitely highlight whatever your answer is, so I know that that's what you're talking about. Okay, so now we're going to look at the next one. So I have an element, and it has a half-life of 90 seconds. If 1 million atoms of it were prepared, how many atoms would remain after 4.5 seconds? Ooh, this is a little bit trickier. So instead of mass, I have atoms. And I'm going to go ahead and get rid of all this stuff. All right, so I've got 1 times 10 to the 6th, and this is atoms. I've got my 0, 1, 0. I have to go, it tells me what the half-life is, and it wants to know how many would remain after 4.5 seconds. So that's when I know when to stop, when I get to 4.5 seconds. So I'm not going to worry about this time 10 to the 6th for right now. I'm just going to take the 1 and go 0.5 and just know that it's going to be times 10 to the 6th. The time that has passed is that 90 is 0.9 seconds, so 0.9, and that's seconds. I have half of it gone, 1 half-life. I'm going to split that 0.5 again, so it's now 0.25 again times 10 to the 6th. I have 1.8 seconds that have gone by. I've got a quarter of it left, 2 half-lives. I split my 0.25 again. I add a 0.9, so now I have 2.7. Got 1/8. 3 half-lives have gone by. Split again, do the same process. Add my 0.9, so I'm at 3.6. Add a 16th, 4 half-lives have gone by. One more time, 0.03125. And finally at 4.5 seconds, that's my stop. I've got a 30 seconds of it left. 5 half-lives have gone by. I look back at my question. It's asking me how many atoms remain. So I know that I need to make sure at this point I include my times 10 to the 6th. And this is my answer right here. Okay, let's look at the graph. All right, so here's your graph and here's your data. You're gonna put time on the x-axis. So time usually goes down here. Oh, wonder why it won't let me. Oh, there we go. Okay, so here's time. And then if you notice, there's activity. Activity means that you're measuring the amount of radiation that's coming off of the radioisotope. And there's different types of ways you can do that. This is called counts per second. So essentially it sends a signal. The amount of activity it has, it's like a signal that is generated every second. So that's what's going to be on your y-axis. So this is going to be counts per second, so over here. And when I go ahead and do this, I'm going to make my scale. Of course, up here will be 800. That's counts per second. I can go, if I look at this, I'm not going to be able to count it exactly right here, but it's about 10. And if you look at the key, it will show you. I got 10, and this would be in days. So 10 days is right there. And if you were to graph it, it would look something, let's see if I can do this right, something like this. So how do you determine the half-life from this graph? Well, if your top number is 800, you take half of that. So 400, let's say 400 is right here. You come across 400, come across, and you drop down straight. And in this case, it looks about like 5 days according to this graph. If you really do it, it turns out to be about 3 days. So yeah, so that's how you would determine it from a graph. All right, let's turn the page to page 12. I'm going to do just a couple of these because I don't want to make the video too long. And then you guys can go ahead and practice. And remember, the key is online, both on OneNote and under files. Okay, so let me get rid of this stuff. Well, I just want to clear it. All right, so that's mass. All right, so let's do number 8. All right, so for number 8, I have 500 grams of strontium-90. In strontium-90, I know we just did a slide about strontium-90. Strontium-90, the reference table has been changed over the years, so now its half-life is 29.1. Rather than 28, which was in the notes just a minute ago. So I'm starting with 500 grams. I do my 0, 1, 0. And I'm looking to stop at, well, how long does it take to get to 125? So I'm going to stop when I hit 125 in mass. So first one is 250, 29.1 days, or sorry, I think it's years have gone by. Actually, let me just check that, make sure strontium-90. Yeah, it is yours. Okay. I'd have half of it left, and that's 1 half-life. So now I divide by 2 again, I get 125. I can stop here because that's what the question says, you know, you want to stop right there. I add another 29.1, so I get 58.2. I have a quarter of it left. And that's 2 half-lives that have gone by. So how long will it take? Well, this would be years, 58.2 years. Right there. All right, let's go ahead. I'm going to go upward now. Let's do number 4. So in number 4, it's asking for fraction. Again, there is no mass. So I can just put X's here. I don't need to worry about it. I still need my 0, 1, 0. I'm looking at P32. It tells me, well, I have to look up its half-life. The half-life on table N is 14.3 days. And after that first half-life, I'd have half of it left. I add another 14.3 days and I get 28.6. Now I have a quarter of it left. 2 half-lives have gone by. I need to keep going until I get to 42.9 days, which is the next one. And now I have an 1/8 and 3 half-lives have gone by. And when I look at the question, it asks me what fraction. So this would be my answer for number 4. Okay, I am going to go ahead and stop there. If you guys have any questions, be sure to email me and let me know. Have a good day. Oh, actually, this isn't the last. There's one more video. Whew, one more.